I'm going to explain briefly the diffusion equation, which is a partial differential equation used to describe how a quantity such as temperature, concentration, or mass diffuses over time. Simply put, this model studies the diffusion of matter or energy in a medium such as solid, liquid, or gas. Why am I interested in studying diffusion? This is because the diffusion terms in the Navier-Stokes equations refer to the transport of momentum or energy due to molecular or turbulent diffusion. The finite difference method is particularly useful for solving the diffusion equation because it is easy to implement and computationally efficient. It can handle complex geometries and boundary conditions, and it can be applied to both linear and nonlinear diffusion problems. In this video, the main aim is to provide the required knowledge on using the finite difference model, which can be used in general for studying the diffusion equation, as mentioned. Since the motivation is to better understand the Navier-Stokes equation, I start to explain the problem in the frame of advection-diffusion model. In advection-diffusion model, we have two important terms that describe the transport of momentum, heat, or mass in the fluid medium. The transport is carried out due to a combination of advection and diffusion. Advection refers to the transport of the matter by the motion of the fluid with a velocity of u, as shown in this formulation, while diffusion refers to the transport of the matter due to the random molecular motion. Numerical methods such as finite difference or finite element methods can be used to solve the advection-diffusion equations and obtain an approximate solution for the concentration of a substance. However, we will briefly study the finite element method in this video. The finite difference method, FDM, is a numerical technique used to approximate solutions to differential equations, which are mathematical equations that describe the behavior of physical systems. FDM is commonly used in the numerical analysis of partial differential or ordinary differential equations, which are used to model a wide range of physical phenomena such as heat transfer. In this video, my main objective is to demonstrate how to approximate solutions to differential equations along with some boundary conditions at the edges of the domain. Generally, many problems do not have analytical solutions, and we need to solve them using methods like finite difference. I will demonstrate in a simple way how to replace finite difference approximations with the derivative in the differential equations. This operation will give a large algebraic system of equations for both the problem differential equation and its boundary conditions, which can be solved using a computer. Here we are using our prior knowledge to approximate the derivatives of a known function f based on its values at two given discrete points. Later on, I will explore the finite difference discretization in more detail. Suppose we have the values of known function f at 3 points, as shown in this figure. We assume that the distance between two adjacent points is the same and equal to delta x. The distance between xk minus 1 and xk is delta x, and the distance between xk plus 1 and xk is also delta x. And the distance between xk minus 1 and xk plus 1 is 2 delta x. The derivative at xk is actually the slope of a line connecting, for example, xk minus 1 and xk, as shown by this formula and the red line in this figure. Similarly, we can approximate the slope at xk by using xk and xk plus 1, as shown here by the green line. We have seen two obvious choices to determine the derivative of a noun function at two adjacent points, as shown by red and blue lines in this figure. But what if we use points xk minus 1 and xk plus 1, at which their distance is 2 delta x? The slope of a line connecting these 2 points naturally provides another approximation for the derivative at xk. It is clear that for this given function curve, this slope provides a better approximation than the two other one-sided slopes. The central slope is in fact the average of the two one-sided approximation as shown in this formula. Okay, we have seen there might be different variations of FDM depending on the type of differential equation being solved and the specific discretization scheme used. For example, for one-dimensional problem, at a given point along with its two neighboring points, the central forward and backward difference schemes can be used to approximate the first-order derivative of a function. Please note the notations used for discrete values of a function f at a given point xk. It can be shown either as xk or fk, as well as through this notation. Based on developments we have covered so far, we are now able to study several key features of finite difference, such as its accuracy and higher order approximations. Let's dig into the problem. When using FDM to solve differential equations or differential operators, we approximate the derivatives of the function at each point using finite differences. However, this approximation is not exact, and there is always some error involved. This error is known as the truncation error. The truncation error can be calculated as the difference between the exact value of the derivative and its finite difference approximation. The magnitude of the truncation error depends on several factors, such as the size of discretization interval, the order of approximation scheme, and the smoothness of the function being approximated. In general, the truncation error decreases as the discretization interval delta x becomes smaller and as the order of the approximation scheme increases. To approximate functions and estimate the truncation error, we use Taylor expansion to expand the function values of f in a Taylor series about point xk here, in both in forward and backward directions as given in these formulas. These expansions are valid if the function f is sufficiently smooth. The forward and backward finite difference approximations for the first order derivatives are given here, as you see. We can obtain the discretization error, which for the forward case is given by this relation. If delta x is sufficiently small, all higher order terms approach to zero, and the first term becomes dominant with respect to other negligible terms. We say that the finite difference approximation is of order h, denoted as OH. So far, we have discussed slopes or first order derivatives. We can extend this idea to higher order derivatives, specifically the second order derivative, by using values of the backward and forward derivatives as shown in this figure with different color codes. The yellow color represents the backward difference and the green color represents the forward difference. The green point shows the derivative of f at the midpoint between xk and xk plus 1, while the yellow color marker resides at the midpoint between xk minus 1 and xk. These two derivative values are located at a distance of delta x from each other. The slope of these slopes approximate the second order derivative of f at xk as shown in this formula. To conclude and enable estimation of the error, a finite difference approximation using Taylor expansion is presented here, which yields the corresponding algebraic equation as shown here. Now, let us consider an ordinary differential equation containing a couple of differential operators on some interval along with boundary conditions. We can use finite difference approximations of all differential operators at discrete points for both the governing differential equation and boundary conditions to obtain the algebraic equations of the problem. In the following, I will illustrate this by applying finite difference approximation to two steady-state ordinary differential equations with different boundary conditions. As the first example, consider following ordinary differential equation along its length and some boundary conditions at each end. This type of boundary condition is called Dirichlet boundary condition. This is a second order ordinary differential equation with two given boundary conditions on interval 0 and 1. This problem is also called a two-point boundary value problem, since boundary conditions are given at two distinct points. We will attempt to compute a grid function consisting of values on discretized points xk and the mesh width of delta x, that is the distance between grid points. We use central difference approximations for both du dx and d squared u dx squared and replace the finite difference equations onto the differential equation and its boundary conditions. After some mathematical arrangements, we obtain this algebraic equation for the main differential equation. From boundary conditions, we obtain the algebraic equations as follows. In this slide, we trace all algebraic equations to summarize a linear system of n+1 equations for the n+1 unknowns. We write the obtained linear system and write them into the following matrix form. We can solve this system to obtain the solution U at finite difference discretization points. We have a new unknown un plus 2. At point xn plus 2, that is outside our computational domain. To solve this, we add this point to our discretization points. Therefore, we have two conditions for k equal n plus 1. One is for the main differential equation as shown here, and the other is for the differential boundary condition as can be seen in this line. The final linear system of algebraic equations can be written in the following n plus 2 by n plus 2 matrix form. In the next slide, I will provide a simple Python code to solve this problem. This is a simple Python code that may not be optimal in terms of programming, but it provides good insight on how to implement the second problem. After importing the required modules, we determine the number of segments n equal 32. We then generate discretization grids in this line and set the width of the uniform interval here. We organize matrix A by setting the diagonal value to minus 2 plus dx squared and the off diagonal values to 1. We carefully set the boundary conditions in these two lines and organize matrix B accordingly. We solved the linear system containing all algebraic equations in this line. We then plot matrix A and you can follow the color code to see this tri-diagonal matrix with boundary rows here and here. Finally, we plot the solution and compare it with the exact solution. You can study the error and other important features of approximation using the exact solution later.